All right, my friends. Hello and welcome to another episode of the AI Show. We are live, and I am excited to be here. My name is Seth Juarez, and we're going to be talking about some amazing stuff today. So I am monitoring the chat over here. Everyone, if you want to talk at me, I will listen to you. Hey, any languages that'll be taught from Yechezkel? You know, I have such a boring name, Seth. Wish I had a cool name like you. Any languages that'll be taught here, I'll show this. I will speak mostly in bad English. Apologies up front. Yeah, we'll be looking at Python in the latter half. In the first half, we're looking at an amazing toolkit that I think is language. They'll tell us language agnostic, but we mostly do Python stuff if it's data science. But they're smarter than me. They'll tell us. From Alfredo, hello, good people. How are you? I added good people, Alfredo, because I think that's what you meant. You know what I'm saying? Hello, good people. I am great. It's a Friday. I'm excited to have a weekend. If you don't have a weekend, maybe you can have a week hour end, to yourself. Self-care is important. Microsoft developer lurking about. I will also be answering the chat. So if it's snarky and funny, definitely not from me. From Microsoft developer. We will have to unmask who they are at one point or another. We don't know who they are. Any thoughts on Python versus Julia versus Rust? Yes. I have a lot of thoughts about a lot of things. My sense is that you should use what makes you happy. You'll find a plethora of things more when it comes to data science in Python, although Julia is an amazing up-and-comer. And the thing that I never liked about C++ was cleaning up after myself. Generally in life, too, I don't like cleaning up after myself. And so Rust makes it easy for me to stay true to my principle. Because it makes it on to clean up after myself. Great question, Mohammed. Here's one. I got some owl goodness just before this. Channel 9 snarky chat. That's right. We got you with the snark. But I will tell you, if we can go here to my twofer because I'm going to write out what we're doing today with the equipment that I didn't need, but makes the show better. That's what I tell my significant other. She's like there's a box outside. Because you know how some of us, we order stuff and then we're like, wait outside because everyone's at home. And we wait and we're like, is there a box coming today? And then when one shows up, my significant other's like, is that for me? So I try to intersperse, things for her and things for me. All right, let's get to the business at hand. Number one today, we are going to be looking at how to do error analysis in AI models. It is absolutely bananas. Error analysis with my friends Besmira and Mehrnoosh, who are fantastic. And they're going to show us how to actually find errors. And I'm going to ask the hard questions. So this is going to be our AI show. And by the way, this is your first time. Generally what happens is we used to do this AI show thing where we would like record them and then release them. We decided to start recording them like sort of live because we'll cut this episode, this part out, the error analysis part, and we'll put it on channel 9.msdn.com if you want to go see there, and our YouTube channel. And you'll see like the pristine one because the marketing folks like us to have a pristine cut. What you're going to see here is me trying to make a pristine cut, but failing. And hopefully you enjoy yourself while you're doing that. And the cool thing is Besmira and Mehrnoosh were kind enough. I asked them beforehand if they could stay after to answer this live studio audience's question. And they said yes. And if they didn't, maybe we can like peer pressure them into sharing the knowledge that they have. That's the first thing we're going to do. This is awesome. We'll put a star on that because I'm super excited for that. All right. Someone's trying to tell me something. Okay. And they're worried because like for the show that's in 2 weeks, it's actually stuff we're not allowed to talk about. We're not allowed. So what I did, they're like, oh, we're getting you a new card right now. So what I did is I did this. Here, I'll show you. I think it's overlay 4. Join us Friday, March 5th for our Learn TV live stream. Secret stuff, capabilities in Azure Cognitive Search. Okay, here. Secret stuff. So they're worried that I'm going to spill the beans. I will not. That's why I make the medium to small dollars. Because I'm good at not sharing things when I shouldn't. Let's get back to number 2 here. Once we're done with that, this is the highlight. This here is the highlight, of course. We're going to do this here. And by the way, keep your comments coming. I will intersperse them. I won't intersperse them when we're doing the show, but we'll get them in after, of course. And then number two, we will continue with our world domination by building the most important social media platform ever. A place where people can play together, rock, paper, scissors. Last time, we got to the place where I started building the model and we saw at the end, it's like, wow, that's some garbage accuracy. But we're going to let it run through some epochs today. And then you'll see that it's going to get better. And as it's running, because this is like the unvarnished truth of what AI is. As it runs, we'll take a look inside of the models themselves. We'll get glitter everywhere because obviously inside of AI models, they're full of glitter and rainbows. And so when we crack them open, we're going to get it everywhere. And then we'll take a look at how they actually work from a mathematical perspective. So those are the two things that we're going to do here. So number one, we'll do the first, we'll say part A, because I can't do this too many times. So part A, build model. We'll do part B. We'll do some inference, which means that a prediction. And then finally, C, we'll look inside. And then our time will probably be up. I asked them to give me more time. And so soon, I may have 2 full hours of the AI show live because everyone's been asking for it. Well, mostly just me. So there you have it. And like I said, I am monitoring the chat on all the channels that we're pushing out on. If you're on Periscope or YouTube or Learn TV, like if you're on Learn TV, I have it right in front of me right here. If you're on any other ones, I have it over here. Right? So, by the way, I'm telling you, they're watching us. No secrets today, Seth. None. So, and like I said, I here you can see, I literally covered it up. Secret stuff, capabilities. So, we got this. All right. I think we are good to go. If there are any questions, just I keep hiding behind my screen here. If there are any questions, please make sure to get them in. This show is designed for us to feel like we're hanging out and learning some stuff. And so if I'm going too slow, let me know. If I'm going too fast, also let me know. Basically, just let me know if everything's... And if like all of a sudden I'm blurry because my upload speed today feels a little garbagey, let me know. But maybe it's better that I'm pixelated. Maybe. All right. And with that, let me bring in some guests here. Pow! Hello, Besmira and Mehrnoosh. How are you doing, my friends?
Hello, hello. We're doing well. Yeah, great.
Okay, this isn't the official part of the show, so we don't have to be super serious. But once it's time, serious. I'm so glad you could be on here. Are you okay staying after answering some questions?
Absolutely.
Okay. Cool. All right, so people are saying stuff. They will be more snarky if there is a secret for sure. Yeah. They are right now. There's like people teamsing me as we speak. Do not share. Ivana is here. Hello, my friend. Espero que todo esté bien. Look at that. Trying to feel international here for a second. I only speak English not well, and I also speak some any foreign languages amongst my friends here.
Yeah, Italian, Albanian,
Italian. All I know how to say in Italian is molto bene. Mi chiamo gelato.
Good job, Seth. All the useful stuff.
What did I just say?
You want to have an ice cream?
Mi chiamo. I thought I said my name is ice cream.
Oh, I see. Oh, yeah, yeah, maybe that's not correct. Your name probably is not ice cream, but
I wish it was. More people would like me.
That's true. Think about it.
Yeah, you know what? It's true. It's true, Seth. And let me. Everyone's like, it's true, Seth. It's true. Oh, let me turn this up. I'm trying to play my sound effect. It didn't even work. Hold on. Oh my gosh. Like I totally messed up my sound effect. Oh, my program froze.
It is. It's because of the ice cream.
It's because like she like dove in. She's like, you're right, Seth. She's right. Like my mom really liked me for a time. And then obviously. All right, let's see if it's working now. Yay! Did that work?
It did.
Is it loud enough? Because sometimes people are like, we can't hear your sound effects. Here, let me get like my thought. What did you say about me, Besmira? I thought we were friends.
We are friends.
Oh my gosh, I even like fake teared up a little bit. Did you see that?
No, do it
That's
again.
why I went to the theater. I was an actor. All right. Sorry. Okay, we should probably. I think the marketing people are here. We should probably do our show. Hold on. Let me make sure. So, just some instructions as we do our show. I don't need this thing anymore. It has served its purpose. Mehrnoosh, can we get you to share your screen? Make sure that works. We'll set this up here.
Yeah, absolutely.
Okay, and then. By the way, wasn't that a cool music? Like it was like very.
Sorry.
That's okay. Yeah, and then I minimize that other thing, and so what we'll do, friends, is some instructions as we do the show. So what I'll do is let me make sure this works. Is I'll be like, maybe I'll go solo. You're not gonna want to miss this episode of the AI Show where we talk to Mehrnoosh, Sameki, and Besmira. Oh, Besmira, Nushi. I didn't. Since me and Besmira are on first name basis only, where Mehrnoosh and Besmira talk about. Hold on, let me get the title up. Gosh, I'm horrible at this. Not that. We want the banner one. Building responsible AI using the error analysis toolkit, and then I'll be like, pow. No, that's not it. Pow. That's what I'll do. And then we'll do the chat. Okay. Does that work?
Yep.
Yeah.
Gosh, it's okay. There's literally like my mom is here and that's it. I'm looking at your screen and I see Mehrnoosh, our faces.
Yeah, I will switch to this one. Do you want me to remain on this one?
Yeah, let's you don't have to. And then also you got to hide that thing. Hide. There you go.
Sure.
There you go. Okay. All righty. Are we ready, my friends? Let me get my stuff going here. And again, just some tips as we do here. I'll turn the music on. Just some tips. You got to look right at the camera when you're talking to me. You're going to want to look at the screen, but don't do that. It'll look like this. That's a great question, Seth. Let me tell you more about, it'll just feel weird. So look at the screen. And then if you run out of things to say, just stop talking. Any questions?
Awesome.
All right. It's going to be good. I'm going to turn all my other sound effects off because now we have to be serious. All right, here we go. Oh, look. Mohammed has a question. We'll save this one for last. I am writing a thesis and willing to take area equals AI ops about topics, thinking data, or anomaly detection. Do you advise any other immersion topic? Yes, Mohammed. I advise error analysis. This is good stuff. Like, I'll be honest with you. And let me go on my little pre-rant here. Nobody knows what these things are doing, not because it's not find outable, but it's because they're not looking. And so a lot of the inequities that AI causes is simply due to human laziness. How about that for the knowledge, right? Human laziness. And so we're going to learn today how we can undo that, because I saw a preview of this the other day and I was like, yes, this is great. This is great. All right, Alfredo's ready. So we got to start. Once Alfredo's ready, we all know. Let me get a sip from my orange drink here. One day I might reveal what's in it. No alcohol. I don't drink alcohol because, I mean, could you imagine? Like, I'm already weird in general. Imagine me with alcohol. Oh, be a horrible show. Or you could not look away. I'm not sure which. Okay, serious. Now we're serious. Okay. Here we go. Let me time this. I think it's overlay 5. No, it's not. Overlay 5. That's it. Okay. All right. So I'll start here. No, we'll start with the 3, with the 3 shot, and I can't forget to put the banner up. I'll put the names on, and y'all ready?
Yeah.
Okay, we're gonna look straight ahead. Overlay 5. That's it. Okay. Here we go. Serious. You're not going to want to miss this episode of the AI Show, where you get to look inside of AI models to figure out where the errors lie. It's not just about fairness. It's not. Oh no, it's fairness. What's the other one? Interpretability. Okay. I got it. This is gonna be good. This is good. Okay, straight face. Overlay 5. You're not going to want to miss this episode of the AI Show. We're going to look at the error analysis toolkit so we can look inside of AI. It's not just about fairness. It's not just about interpretability, but it's about finding errors. You're not going to want to miss it. Hello and welcome to this episode of the AI Show. We're going to talk about, and let me put the title up here so you can see it. Building responsible AI using the error analysis toolkit. I've got Mehrnoosh and Besmira. How you doing, my friends?
Great. Thanks for having us.
Awesome. So let's start with just a simple introduction. We'll start with you, Besmira. Tell us who you are, what you do, and then we'll talk to you, Mehrnoosh.
Hello, everyone. Yeah, I'm Besmira. I'm a researcher at Microsoft Research. I work, broadly speaking, in responsible AI and human-centered AI. Thanks for having us, Seth.
Fantastic. And you, Mehrnoosh?
My name is Mehrnoosh Sameki, and I'm a senior program manager on the Azure Machine Learning Responsible AI tooling team. Very excited to be here today.
Awesome. So we'll start with you, Besmira. Let's talk about, if you will, maybe just a tiny review of what of an AI model is. How do we know if a model is doing well? Sometimes it feels a little black boxy. What say you?
Yeah. In fact, like in machine learning, we deal with 3 different things. We deal with the data that we want to learn from, and then we have an architecture or an algorithm that we train to learn from the data. And after we train, we come up with this model, and you could think about it just as a function, like something that takes as an input some data and gives you a prediction about that data or a transformation on it. Now, when we evaluate these models, of course, we evaluate them on the training data and we say how accurate it is. But in the best case, we should have some sort of test data that ideally comes from the real world. And we measure accuracy or error rate in that test data. And we give these numbers. You might have seen all these articles saying that, oh, this model is 90% accurate in this particular benchmark, or this model reached human parity, which is sort of like a bold statement, if you ask me, in a particular task. And we think that this type of evaluation, when we just give you like one number about how the model does, is sometimes perhaps not sufficient in order to think about the nature of errors, how different they are from each other, and the source of that.
So it's interesting because I love the way you phrased it. You're saying that AI is like a function, except we don't know what's inside of it. And the only way we know if it's good is we hold out some data and we say in aggregate on the data we hold out, it's N% accurate, or it has N loss or whatever. How do we get more fine grained? Because I feel like if you're going to put a function out there that you don't know what it does, you should probably know a little bit more about what's happening. How do we get more fine grained?
Yeah, so the secret, which is not as much of a secret since we were talking about secrets before, is to actually look down in the data and say, how can I slice and dice this data in meaningful ways so that I can actually evaluate model performance and accuracy in all these different pockets. And very often there may exist pockets in the data for which our model doesn't do as well as the aggregate accuracy. And the question is, like, how do we find them? You may do it two ways. You may say, okay, I have certain dimensions that I care about or features, and I can evaluate the model on them. Like if I'm building a traffic sign detector, I can say, maybe I want to see how this performs during different times of the day or in different weather conditions. And these are all dimensions that one may care about. But then sometimes there are just like too many dimensions. And it is hard for a developer to think about all the possible combinations where error may be more, more represented. And so we think that it is good for developers to have the help of automated tools that can guide them through these pockets without them thinking about all these possible combinations. And that's exactly actually what Mehrnoosh is going to show later.
That's interesting. I see. So basically, what's the difference between this and maybe interpretability and fairness that we've talked about before?
Right. So we think about all these aspects of machine learning as actually like a large family of tools and properties that a machine learning model needs to have beyond accuracy. So basically, as a community, we need to sort of like go beyond evaluation in terms of like just mere accuracy or automation accuracy, but also think about all these other aspects. And if you look at this from the perspective of reliability, when all these models or make mistakes, these errors can impact the user experience or even, society in different ways. It may become a safety issue. For example, if that traffic sign detector is hallucinating a green light when there is no green light, then it can become a safety issue. If it affects or if error is higher for certain demographic groups, then it becomes a fairness issue. And then sometimes it may not be about safety, it may not be about fairness. It may just be that you are going to a grocery store, you're using an app, a computer vision app that tells you more about the product. It tells you if it is fair trade, it tells you if there is a sale, and it works well for apples, but it doesn't work well for oranges. And then you lose trust on it. Like you are not going to use a product that only works on only one type of fruit, right? So you lose trust on the app. And maybe you lose trust on machine learning altogether because you may think this is just something that is cool on paper, but not in product.
I see. So this is more like you're saying that fairness and interpretability, it can be subsets of just general errors overall, because it might not be a fairness issue. It might just be that you're not measuring things right. Is that what you're saying?
I'm saying that, yes, exactly, that they are part of the overall debugging experience as well. Like interpretability is a great, means for doing further diagnosis on the model. And basically, you can go back to the data or back to the model. You should be able to do both.
Awesome. So let's go to you, Mehrnoosh. I feel like we've talked about this enough. Can you explain like what the toolkit actually looks like and how people can use it?
Absolutely. So I'm just going to walk you through a little story which has been trained on top of census data, which is a binary classification example that predicts whether people would earn more than 50K or less than or equal 50K. And I'm going to show you different parts of this tool: identification of errors and diagnosis of errors. So very easy. You can just pip install the responsible AI widget. So pip install RAI widgets and the tool is yours. Here I'm just starting with the census data, doing stuff that any data scientist would do, like trying to clean my data and apply some feature transformations. Say on numerical features, I'm doing simple imputing and standard scaling. On categorical features, I'm doing simple imputing and also one-hot encoding. And so after that, I split the data into train and test. And I train a machine learning model. In this particular case, I'm just training a light GBM classifier with 50 estimators. And after I fit my model, I can call any of the interpretability techniques that we support in the Interpret ML open source offering, specifically in the Interpret-community repository underneath that. Here on top of the model, for instance, there's SHAP that you can use. There is global surrogate models. In this case, I'm just using a mimic explainer. And so this mimic explainer is supposed to bring an intrinsically interpretable model to explain your original black box model, if you will, which in this case is this light GBM explainers. After I get this explainer object, I can call explain global to just like understand what are the top K factors that are overall important for making the predictions of whether someone would earn more than 50K or less than or equal 50K. And I can also call explain local on it for understanding individual predictions or individual explanations behind predictions. However, the topic of this show is after you generate that explanation and the global explanation object, you can pass this to the error analysis dashboard, which is what we are discussing today, alongside with your dashboard pipeline, which I just created, consists of my basically featureization process and feature engineering process that I just defined, if you remember, numerical features and categorical features and how they transfer, and also my model training. And the other things are just like the ground truth values and the prediction values. And so once you pass these to the error analysis dashboard, it will load this dashboard for you, which I just, for simplicity of seeing that, I opened in the new tab using this full screen. And so let's see what we are looking at together. As we said, the first stage of this tool is about identification of errors. And for that, you have two different modalities. First, you have this tree map, which is basically an error tree map that takes your data, your ground truth values, and your prediction values, and creates this sort of hierarchical clustering of the data into interesting but also interpretable subgroups. Now, it's interesting because they have different error rates, and in some categories, like the right-hand side of this tree, they're a lot more error-focused in cohorts compared to the right side of this tree. And interpretable because you, for instance, can click on any cohort. For instance, I just clicked on this cohort, and I realized that 25% of people in this cohort have received error, and then this is in charge of almost 50% of, or this cohort, this node is in charge of almost 50% of the errors that are happening in the overall data. And I can also see what that cohort is about. That cohort is about people who are married, they are lower education, and they are on the older side, age greater than 33. So these are married people, later phases of life, who do not have a lot of, or have less education or lower education. I can also click on another node, for instance, and see that this node has 28.75% error rates, meaning 28% of people in this node, which are people who are married, younger age group, and higher education. So 28% of these people are getting errors, and this node, this cohort that I just defined, is in charge of 5.5% overall errors. So not much in terms of coverage, but still 28% of these people are seeing errors. And so you can click on a variety of these nodes, and the great part is you don't have to do anything. This tree is actually trained on top of your model errors for you, and you can just come and investigate and understand nodes and cohorts with sort of different proportions of errors. The other thing you can
sorry to interrupt you, but this is
absolutely
like you are going so fast, and this is just, I want to hit this. Basically, what you're doing is you're showing how this function that was learned, not written, how it actually makes decisions, but more than that, where the errors are in the decision. So, for example,
exactly.
when you're saying an error, you mean it's mislabeling some test data, basically, yes. And you're showing here the cohorts of the data where the mislabeling has happened. Am I getting this right?
Exactly. And so imagine if you don't have such a tool, you cannot possibly combine all, combination of features and put different thresholds on continuous ones and then combine them all in different variety of ways in order to understand where errors are focused. That's not just scalable for you. And so this tool just puts it in front of you. It tells you these are the cohorts that most of the errors are focused in. And so now you can, for instance, take them to the diagnosis part to understand why this cohort is making or is seeing a lot of errors in it, which I will showcase to you momentarily.
Awesome. So basically, it could be like a simple like these are the ones that it just flat out got wrong. Let's investigate why.
Exactly.
Sorry, and continue. Sorry to interrupt you.
No. This is perfect, and would love to get interrupted again. Please do. So when I click on feature list set, another thing that we can see together is what factors led to more errors, or what factors were more indicators of errors in the model. So for instance, I can see relationship, marital status, and age are the top 3 factors that contributing to the errors that you're seeing in this decision tree. And another cool feature is you can, for instance, uncheck them or unselect them and retrain your tree. Imagine you don't want to include one feature. You can unselect it and then retrain your tree. So it's absolutely adaptable to what set of features you would like to use on top of it. So here, this is what I'm going to do. First, I'm going to select this cohort. This seems to be people who are married. I'm going to save this group, and this, as you saw, it's also an erroneous group. So I'm going to call it married error so that I know that this was my erroneous cohort. 81% of the models overall errors are focused in this node, and this node, 22% errors are happening inside it. I'm also, just for the sake of comparison, going to click here. This seems to be people who are unmarried. And as you can see, the error rate is low. Only 4% of people are getting errors here. And this node is in charge of 18%, which compared to 80-something%, it's a lot lower. So I'm also going to save this cohort for a later time for investigation. So I'm just going to set not married. So before taking these two cohorts to the explanation part and try to diagnose why one is getting more errors and why one is getting better results so that we can go and actually improve the situation for those individuals who are married and are getting erroneous labels, I would like to add that there is another view that you might like. So this view is called heat map. That's for when you have up to 2 features in mind that you would like to investigate. For instance, what are the different error rates that are happening in the sub-cohorts attached to that feature? For instance, first I select education num here. So I can see, Seth, that as people are more highly educated, the error rate is also increasing for them, for the most part. So basically, as we go through lowest education to the highest education in this cohort, I see that there is sort of a pattern for error monotonically increasing with that like education getting higher. Another thing that I can bring to the picture is I can bring, for instance, gender, because I want to now see how is it work for females and males, which are the 2 values of gender in this particular data set. And so I can first see that there are discrepancies between females and males in each education group. So there's almost 5% more error rate for males of the same education group compared to females. And the same pattern is true across them, that, in that sense that as each group is getting more educated, it seems like there is also error monotonically increasing, and that suggests that there might be a correlation between education and the error that is happening inside this model. I'm not showing that today just for sake of simplifying the scenario, but you can select one or many of these grids and select and also save that cohort and then take that cohort to the explanation phase. For now, I just go to the explanation phase with the 2 cohorts that I identified. Once you go there, you land on 3 different tabs. Data exploration, global explanation, which is like overall interpretability of how the model is making its predictions, and local explanations, which are for individual data points. And then it also includes what if. These are for helping you diagnose what is happening and hopefully informing some of the mitigation strategies that you need to put in place to improve the situation for those erroneous cohorts. My first step would be dataset exploration. I click on aggregate because I would like to understand overall how this not married group and this married error group were different. One had very few errors and one had like almost in charge of 80% coverage of errors inside my model. So the very first thing that I would like to see is I set the y-axis to count, and I set the x-axis to truth values. I would like to see, in terms of ground truths, the actual labels that people had during training, how much I'm representing both cohorts or both groups of labels of less than or equal 50K or more than 50K in my ground truth data. I can see that the data is really imbalanced for the not married group. However, when I go to married group, which had a lot of errors, I see that this is actually pretty balanced. So I have a lot higher values or number of people who actually earned greater than 50K compared to the not married group, which this imbalance was a lot more. And so that suggests to me that when I have so much representation in an almost balanced way for more than 50K and less than or equal 50K for ground truths of more than or equal or more than or less than 50K, then it becomes a harder job for my model to distinguish between these 2 groups, because this data set is not huge and the 2 groups, 2 labels are being represented equally in the training data. So the model tends to make more mistakes in detecting one from another. One possible mitigation would be for you to, first of all, augment the balance of your data everywhere, but bring a lot more labels, for instance, for this group of greater than 50K, or even like equally for less than or equal 50K, to just like teach the model more about the patterns of how to distinguish these people from each other. With a smaller data set, the model tends to make a lot more mistakes because it just can't detect.
That makes, sorry, and I'm starting to understand, because this This is more like, look, I started as a software developer for 10 years. Then I went to grad school and did research in machine learning. This feels like actual testing and debugging kind of thing that we would do in normal software practice. Would you say that it's similar?
So we feel like responsible AI is about rigorous AI engineering. So in that sense, you're absolutely right. Like the same way that we debug our code and we debug our like machine learning life cycle in terms of what hyperparameters go inside it, the same way we have to understand what is happening inside the model's prediction, and no model story is actually complete without the data story. So the data is the input to the whole world of model training, right? So if there are some patterns that we can enhance, augment, or correct in our training data, I believe that our models will be drastically improved as well. But you're absolutely right. It's quite similar.
Cool. Sorry I interrupted.
No, that's a very great point. The other thing that I wanted to mention here is, for instance, I can select prediction values on the y-axis and keep these ground truth values on the x-axis. And so here, I just want to just state it for simplicity of understanding that here you can see that people with ground truth less than or equal 50K and predicted more than 50K. So this is one of the errors that are happening. And also this is another error that is happening. People who had ground truth of more than 50K, but they have got the prediction of less than or equal 50K. And as you can see, Seth, people who actually had ground truth of greater than 50K are getting a lot more errors than people who had ground truth of less than or 50K. And that pattern is true for the overall data as well, not just in the married group. And so one possible thing would be maybe we have to go and bring a lot more people with ground truth of more than 50K, both married, not married, and just augment that cohort so that the model learns to distinguish them better from people who had the ground truth of less than or equal 50K.
I mean, this is awesome. And it feels like if you're more rigorous, because now with things like automated machine learning, you can build a ton of models at the same time. You may find that the aggregate metrics of, like AUC or like error, bias, or variance, those are not enough. And diving in is a little bit more helpful.
Absolutely. And I'm personally a huge fan of adding all these insights to automated machine learning techniques so that as a stakeholder, as a user, you can make a more informed decision as which one is the best model, not based on one aggregate, either accuracy, area under curve, error rate, you name it. Yeah, absolutely right.
That's awesome. Any other things to show us on the error analysis toolkit?
Yes. So 2 other things I wanted to showcase was the global explanation capability of it, which is really the marriage of this tool with the Interpret ML toolkit, which is for machine learning interpretability. And so, for instance, you can see for not married people, the top second most important factor is age. Right? Like age is an important factor in making the predictions for not married group. However, for married group, you can see that marital status is the top one. That was the same for not married group. But capital gain suddenly becomes really important. So in a way, you can see for each group what factors the model is using the most in order to making its predictions. And sometimes they might ignite some interesting questions. Why for my married group, I'm seeing a lot of pressure or a lot of weight is being given or is being put on capital gain versus for not married group, it's on age. And so those are all signals for you to go and investigate the balance of your data and understand better. And one last thing that I would like to highlight, Seth, is the local explanation, which allows you to dive deep on one cohort. For instance, I have this not married cohort here. I could also shift to another cohort if I want to see the married cohort. But it shows you the data points of it that have been correctly predicted, the data points of it that have been incorrectly predicted. And so, for instance, I go to the erroneous cohort in my no married group, and I select one of them just randomly, for instance, like say this one. And I can inspect it and understand what are the factors that are impacting its predictions in positive way or in negative way. So this is the local explanation part. You can also select more than one. But the other cool thing that I can do is I can run this what if analysis panel, and right now this person had actually truth value of 50 greater than 50K, and it was predicted to be in the class less than or equal 50K. And so I can say, for instance, what happens if this person was not divorced and was married? And so as you can see, suddenly the prediction was changed from this to the right one, which is like more than 50K with 80% probability. So you can do a lot of these perturbation cases and further debug your model and see what factors switching and perturbing leads more to changing the outcome.
Well, this is awesome, primarily because it's been such a black box that developers generally are like, how do we even debug this? And so this is awesome. Just to finish up, where can people go to find out more, to learn how to do this themselves?
People can check out erroranalysis.ai. Besmira has also written a fantastic blog that we make sure to put the link here. And reach out to us via GitHub issues if you have any thoughts you want to share, feature ask. We always welcome community contributions. So looking forward to hearing from you.
Well, this has been fantastic. Besmira, anything you'd like to add to finish up?
I just want to call out to all machine learning developers. We're building these tools for them, and we hope to make them more productive, to accelerate the improvements. And so, just reach out to us if you have asks, discussions, anything.
Thank you so much for being with us, Mehrnoosh, Besmira. You've been learning all about how to use the error analysis toolkit on the AI Show. Thank you so much for watching, and hopefully we'll see you next time. Take care. Booyah! My poor son did you see that? My poor son started printing something, and I was like, no, not right now. Did you see that? Did you catch that?
Nope,
or was it?
I
I was sneaky enough. Nice. I had to tell that poor boy to come grab his printing stuff. He was like, oh, poor guy. All right. So I promised everyone everyone would stay and we would ask some questions. There were some good ones, actually. So let me
log in. Let me log in actually so that we can answer some questions.
Okay.
Yeah.
So Kevin Oliver, this is a good question. She's going to go log in over there and hopefully you'll stay with me, Mehrnoosh. Can you describe what the error is? Is it bias or variance in your model? Or is it just straight error, no error? That's for you, Mehrnoosh.
Yeah, so error in this case is just like discrepancy between your ground truth values and your actual labels. So in terms of classification, it's like when the label is not matching the ground truth values. So for instance, you have the ground truth of greater than 50K and you have received the prediction of the other way. In terms of regression, it might be that your actual prediction is a particular threshold far from the actual prediction that you needed to get. So say the housing price was supposed to be X, and now you see that it's like way away from X. So that is what this tool is built upon in terms of error.
That's cool. Another question from Learn TV coming from Pranay. How are the nodes created by this mimic explainer? For instance, one relationship shows up higher in the tree as compared to another.
That is a very good question. So I think these are two questions. One is how that decision tree is being trained. That decision tree was not about mimic explainer. And then mimic explainer, I can explain where it fits.
Okay.
So the mimic explainer part was the part that was powering the global explanation and local explanation tabs. So the way that it works in particular, mimic explainer is you have a black box model. So in this case, I had the light GBM, and then you bring an intrinsically interpretable model that would fit on top of this black box model. And so you pass, say we have this black box, you have the input features and you have the predictions. You get the features and you attach the prediction of the black box to those features as is ground truth, and you pass it to this intrinsically interpretable model and you say, okay, learn how these features have been mapped to the prediction of my black box model. And it will learn it because it is a model. But since it is an intrinsically interpretable model, you can look inside that and understand how it is making its prediction. So that was the part that was powering the global explanation and the local explanation tabs. Now, the error tree is different. It's just a binary tree that is being trained on top of your model errors. And in that case, it's not using the Mimic Explainer. And Besmira, do you want to say more about the tree?
Yeah, the question just for you, Besmira, was how are the nodes created by this Mimic Explainer? For instance, one relationship shows up higher in the tree compared to another. And what Mehrnoosh was saying is that the Mimic Explainer was a different process than the tree building, which is basically just a binary tree that's being built.
Yeah, think about like the simplest way to think about the tree is that the first time when it makes a split, you consider all the features and you see which of those features has the highest information on failure. Like if I were to pick just one, one of them will have the highest mutual information, Gini index. There are different terms for that, but that will be more predictive on failure. So it constructs that first split, and then the second time it does it exactly the same way, but in a recursive fashion, just for the parts that are in that node.
For those that are watching that are hearing Gini and mutual information, just think of it like this: we're basically looking at the answer and how messy it is. And then we look at another column and we look at these two columns together. And if this column makes the messiness of this column less, we find the one that makes it less the most. And then that's where it splits. That's how I understood it growing up, so to speak. It's all about taking away messiness. And that's, I think, hopefully I got this right. Y'all are the experts. Did I get this right?
That's exactly correct. Chaos minimization, basically.
Fantastic. Here's another question from Kevin. Another question, how will this tool work with more secure data using some kind of differential privacy? Now, differential privacy is interesting, primarily because you're constrained by the budget. If you all want to talk about that a little bit, how do you do that?
So there is a few things about, being able to debug data when with eyes off, right? In that maybe you will not be able to look at all this metadata and so on. So something that we often do with our teams is that even though they may not be able to train with that data, they can still use it for just error analysis. So you can pass, perhaps you will not be able to train based on gender attributes, age, and so on and so forth, but you can still do error analysis on it for you to understand as a team where the errors are distributed. So it doesn't have, you don't have to train on the same feature set.
I see. So basically, and that's an interesting way, because maybe people are trying to be responsible and they're like, I'm going to be responsible by taking gender out, when in reality that feature leaks everywhere. And so it's important to test on that as well. Is that a good way of putting it?
Yeah. And you can do error analysis on any type of feature without having to use it in the model.
Fantastic. Well, this is really cool. I was thinking about this. I've been having how you have deep thoughts every once in a while about machine learning. And to me, machine learning is just a way of writing functions with data. But I've always thought about how does the functionality actually map to regular if, else, for loops, whatever.
Oh, yeah.
And since there's no way that currently to do that, as far as I know, this is a really good way of sort of like behind the curtain, tossing things over and looking at what the machinery looks like.
Yeah.
And to me, it's really cool. I mean, is this what you all do research on primarily? Is there more? What should people look forward to in the field?
That's correct, Seth. Just to add something to what you're exactly saying, because sometimes we have similar thoughts as well, right? And the reason why we work on responsible AI and reliability is because we had all these frustrations building algorithms ourselves. And then you realize that by just debugging the code line by line, just as we usually do in traditional software engineering, it just becomes hard to generalize. You look at all the numbers and then you go from one line to the other, and then it's just hard to go one layer up and to understand, is this a pattern, or is this just something that I saw in one execution and then the next execution is going to be completely different, right? So we need to adapt techniques from software engineering, but also we need to innovate so that we actually visualize this thing, we generalize them without people going through 1,000 executions to get an understanding.
Yeah, and I remember one time I was in a research thing, and one of the PhD people was explaining to me, this model is, I think it was when we invented resonant 50s or something, and I remember the researcher was like, And they told me this with some pride, and I was kind of disturbed by it because I'm a programmer first and then a data science guy second. And he was like, and we don't even know what it's doing on the inside. And remember, they used to say that kind of thing with kind of some pride maybe 3-4 years ago, and that kind of disturbed me. It's like, well, shouldn't you know? What if this is something that's going to put someone in jail? Right? And so that to me was disturbing. So this work to me, super important. I'm very grateful for the stuff y'all do. Any call outs y'all want to do before we get to work on our project and y'all can go back to your wonderful days?
I want to answer your other question on like what should people be looking forward to. So we are passionate about extending error analysis on other domains, like for example for images. We have a few papers out. I can paste the links later on like how you extract image features from this data so that you can actually use them in error analysis. It's not in the tool yet. We hope it will be when time comes. But on the research side, there are a few cool things to look out for to increase the broadness of the tools.
And that's cool because with tabular data, it's easy to do stuff. But then when you get to imaging and you get to sound, it's a little bit different. But it's all vectors, all turtles, all the way down, right? So eventually you'll be able to figure out something, right?
Yeah. Eventually, on the research side, we're sort of like set. We just need to do the tech transfer to tools.
Boom. Well, y'all are the best. Thanks for being with us. Everyone say thank you to them. Thank you. This was awesome. And we will see you in a little bit. So thanks for being with us. We'll see you next time, my friends. Well, I'm still going to be here.
Thank you.
Nobody else leave. We're still working on stuff. We'll see you later.
Nobody.
See you later, Besmira. All righty. That was awesome. Now I can turn the music on. That was really cool. I mean, like, yeah, someone actually told me that like a couple of years ago. They were like, oh, I don't like this music. Maybe I should go to the next one. They were like, we don't even know what it's doing. And I'm like, that should bother you. That should bother you, right? I mean, like, imagine writing a function and putting out some assembly if you're doing .NET, or a jar file if you're doing Java, or just some Python files that you're putting out, right? And you're like, I don't know what it's doing all the way, but it seems to be doing the right thing. That feels wrong to me, right? Doesn't it? So, I mean, that's why I think this is super important. And look, here's the thing. I'm not trying to besmirch researchers, because there is some wonder to this. I remember the reason why I got into machine learning originally. I was in Hal Dalmay's class, incidentally, and I don't know if you were there for that conversation, but guests come on like a half hour before, and we make sure everything's kosher and everything's working. That way we can have a semblance of a good show. And we were talking about my advisor Hal, right, and how things like when we did research, there's a sense of wonder. Like I remember the first time I ever saw K-means algorithm. It's a really dumb algorithm. But basically, I watched the computer make its own groups out of points. And I was like, oh, it's thinking. And then I'm like, but it isn't, right? It's just math. And I say maths because in the UK, they have more than one. In the United States, we only have one, right? It's just math here. And I was like both in awe of the thing thinking. And if you don't know what K-means basically you say how many groups you want, and then the computer basically does this optimization, optimization thing where it figures out like how to pack groups together. And so imagine like a SQL query where the where clause, or having clause is basically just group them the way you think and tell me. And I remember watching it do it. And I was like, wow, in awe of that the computer was thinking, but it wasn't. And that's the thing that sometimes we use intelligence for computers as a means to defer liability and responsibility. Like ultimately, if you put functionality out there, you're in charge of it. You can't be like, well, the computer decided. It's the same thing as saying, well, I flipped a coin. Because sometimes, almost the same thing. All right, let's see what we got here. Here's a good one. Does that mean when you don't know what it's doing, you bring them out? Yes, Yes. Anything sufficiently impressive that you don't understand is basically magic. I don't like this marketing approach, and I'm not saying that we do that at Microsoft, because I'm very careful about this and our people are super good. But there is an approach of like saying this thing is magic, and it's not. Which brings us now to let me share my screen again. Add to stream here. Boom. Maybe we can let's see. Let's get to working on this. We were going to do the second part, which is rock, paper, scissors. And to be honest, I haven't even opened it yet since our last sojourn. So let's go over here. And remember, what we did is we repurposed an old thing. I've done talks with tacos and burritos ad nauseum. In fact, if you go to Ignite, there's a session that I'm doing. This is in a week from next. Make sure you tune in, because I'm going to talk about all what's new with Azure Machine Learning. And also, there's some actual cool things I'm doing in the interstitial programming. That's actually quite cool. So make sure you come. So let's go to the food AI thing here. Code. Oh, let's make sure we're in the right. Conda activate torch. If we're doing this all in PyTorch. By the way, just feel free to ask any questions you have. Like, I'm all about the questions. And I got to get my sound effects here going. Yeah, like whenever we talk about machine learning, I feel like it's a little like this. Let's see if it works. Man, my sound effects are not working today. Here we go. Dang it. That was going to be super funny. So just everyone laugh anyways. Super funny. It's just my programs are not working. Everything's broken. Let me close the program here. But yeah, that's the one thing I worry about. People turning AI into magic, because then all of a sudden it's like we're not liable anymore, right? So yeah. Okay. Let me see if I can get my sound effects going here. Boop. And then let me close this, because you're probably hearing blings from my teams. They'll have to bling me on my phone. But anyways, I think I got the sound effects working. So basically, it's like let's talk about machine learning. We don't know what's happening. It's magic. No, I'm not about that, right? It's not magic, which we're going to show today. So let's go to code dot here and open up the code window. The code window. Here we go. Let's close all this stuff. Looks like I was doing other things here. Okay. I think that's what we used before, right? And we passed in our data. We had Rochambeau data, right? Is this the right place? Did I? Yeah. Train and eval. None. Yeah, there we go. There we go. Okay. So there's our data. So let's see how we use this, and let's run it. Okay. The directory to the training and test data. So Rochambeau data. Okay. And then the output. Oh, yeah. The Microsoft developer is putting in the thank you, Mrs. Microsoft developer. Or Mr. I'm going to go with Mrs. because I can. Let me turn the music back on. Okay, so let's run this. CDSR, boom. Okay, Python train -D. Rochambeau. Oh, no. Dot Rochambeau data. Okay. By the way, for those that are wondering, let me just go back here and do like a quick little reminder. We're basically building an AI model to detect, because we want to make a website where people go and they can do like rock, paper, scissors, shoot, right? And then the computer will just watch them. And then it will tell them, you know, what kind of thing it's doing, rock, paper, scissors wise. So, okay. So this is what the pictures look like. We did this really well in custom vision, but here you can see pictures of me doing scissors and rock. Oh man, I only got 30 minutes. FYI. So yeah. So that's what this is. And what I'm doing is we're building a model to just do classification, right? Because it's the simplest thing. And you can see this is it here, but I need to actually start it so that we all can like talk about it too. Let's do the output, minus output, and then I'll do Rochambeau. I'm spelling dot Rochambeau, and then let's just say AI Show Live, because it looks like I've been running models before, just to see if it'll work. We'll call it rock, paper, scissors, RPS. Let's do description. No, let's just not do descriptions. I don't care. Let's do 25 epochs minus epochs. Let's do 25. We'll leave the batch and the learning rate there. Hopefully I put some smart. Yeah. So it looks like batching 4 at a time, learning rate 001, number of epochs. So let's run it and let's warm our hands by the fires of the GPU. So here we go. Okay, there's the thing. Looks like there's a softmax ending. By the way, I put this in there because it makes it look like it's guessing percentage-wise, but it's not. It's a mathematical trick. Okay, so it's going. It's a mathematical trick to make it look like you're getting a percent. Oh, that accuracy is garbage. Holy cow. 37. Okay. Let's see if it gets better. So let's actually go through what's happening, and I'll put this off to the side here, and then we'll get back to it as it goes. Let's just make sure it gets better. So this is basically saying how good is it at guessing pictures. Okay, so it's going up, so that's good. Okay, so let me show you what's going on, and then y'all can ask any questions you have. I think someone did on Learn TV ask a question, so let me go over to that. No. No questions. But yeah, if you have a question on any of the channels, Learn TV, any of them, just feel free to ask, because like I said, we're all about the questions. Oh, Besmira's like, Seth should use error analysis to see where the errors are. I should, but these are pictures. I'm still, you know, the cool thing, and just to point out, because she's right, there's a way with some of these models to do heat maps over the actual pictures to show you where, like, which pixels influenced the outcome, which is kind of cool. I saw this a couple of years ago, but I haven't played with it. So yes, Besmira, I totally should. Looks like I'm using MobileNet. So let me show you what it looks like to actually do the thing. So I'm gonna write some stuff here on the board. You know what I have? I have a thing. Like, we bought this thing so that we could learn together, because this is gonna take a while. You see, it's still going. Notice it's getting better. Notice it's getting smarter. So good. Okay, good. So basically, let me turn this on again, and let me explain, and then you're gonna see what that looks like in code. Oh, I like this one. It's like a video game. Oh, this is how to do it on pictures. By the way, here's a link. This is how to do it in pictures. Debugging a resident. I'm using MobileNet, but yes, that's cool. Okay, so let's go with red here. So basically, I have a bunch of pictures. This is my bunch of pictures. You know, some are rock, some are paper, some are scissors, and then some are none, meaning that there's no, because we need to classify when people are doing these things. And so basically what happens is we take all of these pictures and we convert them into what are called tensors. And if you think about it, a picture is just a bunch of numbers in a cube. And let me explain what I mean. And this is, so we'll do the cube here, and so you can see what I'm talking about. This is going to be the greatest machine learning explanation ever with the worst cube you've ever seen in your life. So basically, when you look at a picture, you're basically seeing like an image right here, right? So an image of Seth. So that's a picture. Oh gosh, this is so bad. But this is an image of Seth. But remember, if it's a color image, you're basically, there's 3 pixels, right? There's 3 numbers for each of those. The red, the green, and the blue. And so when you look at a picture that's, say, 240 by 480, it's more of a square. So let's just say 240 by 240. So I'm not confusing like scales here. 240 by 240. When you're looking at this picture, it's actually stored, well, if we think about the actual like number, because if you're looking at a JPEG, they actually do they do compression, because if their numbers are similar elsewhere, you might as well not store all the numbers because it's just too big. Basically, when you look at the real representation, it's actually numbers. It's like a big cube of numbers. And so what happens is, and let me move this up here, is that these things are batched into 4 pictures, because that's what we're doing, right? We said we're going to do a batch of, look, it's getting smarter. We said we're going to do a batch of, if we go down, when we pass things in, we're saying we're going to batch size 4. So we're giving this thing 4 pictures at a time, and then we're running through all of the pictures. I think we did 25 times. And this is actually what's happening, okay? We basically load up the data sets, and what we do for X here, let me zoom it here so we can see this here. So I want to explain this. And when I zoom it in here, this X is actually one of those pictures. Well, 4 of them, because we're doing 4 at a time. And this Y is the 4 labels or answers. Like this is the first one's rock, the first one's paper, the first one's scissors, the next one's nut. Right? That's what this means. And what we're doing in PyTorch, which is interesting, and this is what makes PyTorch cool, is I can say, put these tensors or these numbers on this device. And for us, it's a GPU, right? So let me scroll up here so you can see. Hopefully it'll let me scroll without. Okay, yeah. Scroll. Here we go. Notice the device is CUDA, which is a GPU. So if I were to go to Task Manager right now, and I were to go to Performance here, you should see. Maybe my GPU isn't doing anything. Oh my goodness, it's not doing anything. Maybe it's not doing much because it's not a big process, right? Oh, there it is. That's the one that it's using. Derf. It's not using all of it, but you can see it's using the GPU. I'm not even using it to its capacity, which is great. But I have a really nice GPU, just to be completely transparent. I have a GeForce RTX 2080 with Max-Q design. Kevin, it says, if you hover over X, does it show the images in the variable? No, it will show a tensor. Right now, I'm running it here. But if I were to run a debug and go, maybe I should do just a quick debug. Let me do a quick debug with the base parameters here, with the food one, and I'll just do like a 1 epoch, so you can see. So this will run another instance of it, and it appears that my GPU is not even struggling. So yes, Kevin, let's do that. Oh, by the way, Kevin's asking, if you hover over the X to show the images in the variable. Let me show you what it does. And I haven't done this before with people, so maybe it won't work. Let's just run through the whole thing. Well, that's a good idea. So let's do this. I will hit F5. And hopefully it's Conda activating Torch. There it is. It's in the right environment. There you go. Okay, so let's go through this one step at a time. So the first thing we're going to do is we're going to do a transformation on the images, right? Because the images, we need them to be all the same size, 224 by 224. And so we're cropping them. This transform in PyTorch will crop them, right? It will do a random horizontal flip. And the reason why is because this is a way of augmenting the data set. So imagine I have a picture of me doing like this. If I'm going like this, it's still a scissors, right? And so imagine like me upside down. And there's also tricks like solarizing images. Basically, if you have 100 images, if you can flip them 4 ways, now you have 400 images, right? And if you can solarize them, right, now you have 800 images. And now, you see what I'm saying? And so it's a way of giving it more data. So then we'll F10, right? There we go. So there's the training data set. You can see it right here. There's the classes. And notice for us, the classes are going to be tacos or burritos, because I'm running this from scratch. Because remember, I'm reusing this to see if it'll work with our other thing. And let's see. Let's go all the way to the bottom. Yeah, it's getting better, but it looks like it's slowing down. Yeah, see, it got dumber there for a second. And I'm also slowing down on the learning rate as the faster we go, and I'll explain what that means. So now if I F10, right, this is the validation data sets. Remember we talked about like, well, what the heck are errors with machine learning? So basically I have N number of pictures that I use for training. And then I have, like, I hold out like 10% to be like, okay, just for sanity check, does it do well on these? Okay. So then there we go. You can see it's initializing using CUDA. I'm doing MobileNet v2. This is the actual model function. I'm moving it to the device. And when I hit print, you'll see this huge thing comes out. This is the function. This is the function. Like, you put a picture in there, and then it will tell you rock, paper, scissors, none. That's what the function is. So whenever you say model, just think of like function, right? Okay. Now, the thing about it is this thing ostensibly will stink the very first time. It will be completely awful. But we need to know how awful it is. Like, we need a way to measure how bad are we at this. And that's what this function does. This cost function, right, tells you how much this model is costing us in terms of accuracy or whatever, or just loss, or is this bad? So that's what this happy little tree does. And what this does, the optimizer, is it takes this loss function with respect to the model parameters, and it optimizes it so that we minimize the amount of loss that we have. And whenever you have a function and you have minimize and you have a for loop, think calculus, right? Basically, the best way to find a minimum of a function is to take the first derivative, set it equal to 0, and there you go. But that assumes that your functions are what are called convex, which means, like, remember when you did x squared in school, there was like a u? It definitely has a minimum. But these functions, this model function and this cost function, are definitely not convex. And so the optimizer is like this hitchhiker through the galaxy of this huge function that literally walks around. Is like, am I at the lowest spot? Am I at the lowest spot? Am I at the lowest? And it does this for as long as you let it. Like right now, we're letting it for a while. Looks like it got to 72% accuracy, which is not super good. So we may have to switch out. We may have to do something. Again, we're doing this all. I don't think I've done this with this one. Okay, so there's the optimizer, right? And then there is this thing called the learning rate. So remember how I told you the optimizer is like this hitchhiker through the wilderness of this weird function trying to find the lowest place? But imagine if you're a hitchhiker and you're in this lowest spot. How do you know this is the lowest of the lowest of the lowest spot? You don't. And so that's a problem. And so there is this thing called a step size. Like, how big are the legs of this hitchhiker? And if the legs are too big, like, they might walk over like a huge minima, right? And so the learning rate is a measurement, or is a hyperparameter, and a hyperparameter makes it sound like it's extra loud. It's not. Or it's extra like, ah. The hyperparameter's job that's what you pass in as a way to tweak the knobs on what it's learning. And the learning rate hyperparameter says how big of a step size do you have. This makes it so that the learning rate, or the step size the fraction of the step size, I start at 0.01. As it gets deeper into the epochs, I make the step size shorter so as not to overstep, right? And we're using what's called stochastic gradient descent, SGD. And this is just a way of like looking at the first derivative, which turns out that in vector space is called the gradient. Or is it the Jacobian? I don't remember. Besmira maybe is still here and she can help us out. But you take the gradient of the function with respect to its current location, right? And then you subtract that off of the model parameters, and then it just goes, and then you just do this forever. Well, until it stops. And then what you do is you loop through each epoch, and each epoch represents an entire pass through the data set. So let's F10 this, F10 this, F10 this. And looks like we're in epoch number 0, right? And then what we're going to do is we're going to train this epoch. So let's F11 into that. Here it is. So now I'll F10. Oh, shoot. I think I should have jumped into that. Yeah, I should have jumped into that. Bummer. What's F here? What's F? Wraps F. Oh, I know what happened. Yeah, so basically I was, you see this thing right here? This is me. Okay, I know what happened. So this is called a decorator, which allows you in Python to run things before the thing is run, right? And this epoch logger, if you notice, is basically wrapping this function, doing some stuff, and is running the function and then doing some stuff, right? And then it returns the right thing. So this is just a. Kevin says I'm right with the gradient. Thank you, my friend. Yeah, gradient. So now what we're going to do is for each batch, we're going to compute the stuff. So notice that we're going through each epoch. So let's F11 into this, right? Oh, by the way, I think I F11. Okay, so this happened again, right? Because I'm wrapping. And what I'm saying is for this batch, if there is an optimizer being passed in, let's zero out the gradients. If there's no optimizer, because I use this function for both validation of a batch or training of a batch, right? So the model is being passed in right here. And for us, that's that big sequential thing that we built. And notice that I'm basically executing on the model. So let's take a look at what's in here. So let's go to debug console. And that's 10 minutes to wrap there, Tommy. This is the X that you were asking about, Kevin. This is the X. And you're like, what the heck is that? Well, it's basically 4 pictures, right? 224 by 224. Notice there's 3 of these because there's 3 pixels, 3 channels. For some reason in PyTorch, we always do channels first. So channels, height, width on pixels. And you can see that's literally what's going in here. Literally, we're going to predict for each of these 4 pictures what the answer is. Let's take a look at the outputs. Here are the tensors, right? Notice, now this is interesting because there's 4. Okay, I wonder why there's only 2. There should be 4. Let's see here. What's the size of this thing? Yeah, there should be 4. There should be a 4x4. I'm not sure why it's doing that. So outputs here. Oh, okay. Okay. So these are the outputs, and then let's F10, and then we'll see the predictions. There you go. Okay. So this is the prediction because we're doing the max. Why is it 4, 4, 4? Oh, okay. No, this is tacos or burritos. Sorry, I thought it was Rochambeau, but remember, it's tacos or burrito pictures. And so basically, since there's 4 pictures, you can see 1, 2, 3, 4. These are the predictions for 4 pictures, and the vector is saying, or the tensor is, this is the 0 position, this is the 1 position. Whichever one is bigger is the one we guess. And so notice that we're guessing 1, so it's a burrito. 1 burrito, 1 taco, 0, sorry, all burritos and then 1 taco. Do you see that? So that's what the output looks like. Oh, sorry about that. I got confused because I'm like, what are we doing? Why is there only 2? So this makes sense because, again, there's 4 tacos or burritos. This, along this axis, this is the 4 different things in the batch. These are the predictions. And you can see when we do an argmax over them, which is what's happening here over dimension 1, we're basically getting the predictions. Now, this is where it gets interesting. The cost function looks at the output and the real answer, because we have the real answer here. Why? Right? This is the real answer. This is the outputs. And the cost function basically finds out how much we're off by. So we'll F10. And this is then what the loss is. This is how bad we are at it. 0.7. And here's the cool thing about PyTorch if you don't know. You're probably looking at this and like, well, what the heck is all of this? It turns out that when you're doing derivatives in vector calculus, that when you have a function, let's just say you have a function like, I don't know, x squared plus 2x, right? If you want to take the derivative of this thing with respect to x, right? It turns out that it becomes like this. Oh, well, no, let me make it even more complicated because I want to make sure that it's even. So we have x squared plus x, and then the log of that. Let's just say the log of that. So from the predicted score to 1 or 0 for the correct value is your loss. Yes. So here's the log. So let's say we're the log. So this is actually, if you look at it as a tree, the function at the top is a log, right? And then inside of that, you have this x squared, and then you have this x, right? But this actually is if you think about it in terms of a function, right? It's basically the square function, and then you have an x, and then you have, x. So basically, any function can be thought of as a tree of operations. And what PyTorch does, which is really cool, is it keeps track of that tree so it can compute the gradients. Because, as you know, let me do an actual loss function. So let's do the sum over x of x, our f of x, which is our thing, minus y quantity squared, right? This thing is called the mean squared error. This is a huge function. Basically, you have the sum function, right? Then you have the f function, which is some other thing. And then you have the actual y, and then you have some other stuff that's going on here. To take the derivative of this function, to compute this function, you go top down. To compute the derivative, you go bottom up. That's why this thing is stored here, because it keeps track of where everything's going. This is different, like for TensorFlow, and I have 4 minutes, because in TensorFlow, it's a static graph. In PyTorch, it's a dynamic graph. So you can have if statements. This is why I can debug this. Right. So now we take we do the backward step, remember, remember we go down to compute up to get the gradients, and then we step on all the things, and then we get an accuracy, and then we return this, and then we print the loss. Let's go to the output terminal. You can see there's the loss, and then we keep going, F5, and then this keeps happening forever. Continue. And then this just keeps happening for every batch. So basically, to go back over, because we're running out of time, and I want to make sure that next time we're going to have to try some other models. Basically, what we're doing is for all of the pictures, we're doing a huge loop over the epoch, over the batches, to see if our model predicts well. And we measure that with respect to the loss function, and then we take the gradient of the loss function to tell us how to adjust the parameters of the model so that it does the right thing. And that's it. And that's what you're seeing, is this happening over and over. You can see, for example, that you can see right here that you can see the learning rate started out then it got bigger, and then it hung out there for a little bit because it's step size. And then you can see it started to get, the learning got smaller as we got closer to the right thing. And so what I suspect is that our mobile net is not good enough. So let's try a ResNet 50. And this actually happens to be a model architecture. So let me go over here and let's go to the output. There's the data. Oh, here it is. AI Show Live. Notice that these, let me go to Reveal and File Explorer so you can see the actual models. These are the actual models that were built. Let's open the Onyx model so you can see it. Here it is. This is it, right? So the picture comes in. Remember I told you it does channels first. 3x224 by 224. Yeah, Kevin's like, hey, TF2 has a dynamic graph option too. Yes, it does. It does. It introduced that in TensorFlow 2 as well. But I think I'm not sure what it looks like. I use TensorFlow 1.4 and then I started using TensorFlow 2, and then I switched to PyTorch just because it was easier for me to conceptualize the whole math because I like the math of it. But anyways, there's the picture that comes in, and these are the parameters that are getting optimized by the calculus. These numbers right here. And so the picture comes in, and it does a convolution over these things, and maybe I'll explain what a convolution is next time. We're kind of out of time. We do a batch norm, and then we another convolution, batch norm, another convolution, batch norm. Here you can see there's some skip layers. The problem that happens is the gradients tend to go to 0. And whenever you have math and multiplication, zeros are horrid. And so notice that these skip layers are introduced. ResNet 50s do this a lot smarter too, by the way. I think this is just a mobile net. And then at the end, you can see that we just do a generic matrix multiply over the thing. There's the matrix. And then there's the bias. And you're like, well, these sizes are different. Yeah, because remember, we have 4 options that we're choosing from. The one we saw when I debugged was just tacos and burritos. And then we do a softmax at the end. Okay. All right. And with that, I think we are out of time. It's been wonderful. Let me just put my overlay for what's coming up next. Thanks for coming, and we will see you next time. Take care.